Welcome to CS225. In this lecture we will be discussing red-black trees. Red-black trees will be in their form of balanced tree that will sort of have a mix of the AVL tree and B tree type of properties. The AVL tree was a binary search tree, and red-black trees will likewise be binary search trees. And so we'll have that principle intact. The binary search tree idea, every node has two children, all the rules we saw for binary search trees. However, this will have the sort of B tree or 2-3 tree idea in it, also related to it, in that the various parts of the red-black tree will be meant to implement the kinds of nodes we've seen in 2-3 trees and B trees. So, what this will actually be based on is a 2-3-4 tree, which we haven't really talked about, and you don't really need to worry about too much for the kinds of things that we'll be doing with 2-3 trees. You focus on 2-3 trees. But if you can imagine an extension to the 2-3 tree idea, there's a concept you could have of a 2-3-4 tree, and all that would mean would be you'd be allowed 4 nodes as well. So remember, 2-3 trees were enabled you to have either 2 nodes, we called those, or what we called 3 nodes, which had 3 pointers and 2 children. So imagine a tree where you're also allowed 4 nodes. You have 4 pointers and 3 children. This was the overflow case for our 2-3 tree. Imagine a tree where we said you're allowed to have this, and if you wanted to worry about the overflow case, this would be your overflow case, where you had 4 values and 5 children. Other than that, all the rules would still apply. That would be a 2-3-4 tree. The rules would be very similar to our 2-3 tree. The only difference is now the 4 node would be legitimate, and what we could call perhaps a 5 node would be overflow. Whereas the 2-3 tree we looked at earlier, the 4 node was actually the overflow case. The only really appreciable difference we'd end up with here is that if the node overflows and you have to split it, what you would end up with would be, when we split the 4 node, when we had a 2-3 tree and we split this, we ended up with 1 value on one side with 2 pointers, 1 value on the other side with 2 pointers, and the middle value would move up. Now, if we're going to split this node, we'd end up with 2 values and 3 pointers on one side, 1 value and 2 pointers on the other side, and then some middle value would move up. So that's the only difference here, is now it would be the same as if we had had even ordered trees for the B tree. You would be allowed to have a split where the 2 halves of the split weren't exactly the same size. And that's not a really big deal, but we wanted you to be able to kind of learn in an easier situation, so that's why we only presented 2-3 trees, and our B trees only had an odd order. That way, whenever you split the node, either splitting a 3 node in your, or overflowing node in your 2-3 tree, or any sort of overflowing node in a B tree, the 2 halves of the split always were of equal size. And so for the 2-3 trees and B trees, we stick with that. However, just have in the back of your mind this idea that you could have tweaked those definitions to allow for the maximum node to have an even number of children, like this, where the maximum node would have 4 children, in which case the overflow would have 5 children, and your split wouldn't quite divide things up equally. That's not a big deal, but you didn't see that before, so I want to show you that now. Other than that, your standard combine and steal rules and for remove and all that, it's all basically the same. Now, the reason I'm going over this is not because you really need to know 2-3-4 trees, but mainly because the AVL tree, or I'm sorry, the red-black tree, will be an implementation in using binary search tree nodes of the 2-3-4 tree, and we're going to talk about that in a moment. And then maybe this stuff will become a little bit clearer. What I want to do first is explain the properties of the red-black tree. Firstly, it's a binary search tree where every node is colored every node is colored red or black. And by colored we mean we need 1 extra bit of info. Because you could say, for example, if that bit holds 0, then your node is considered black, and if the bit holds 1, then you'd consider your node red, or vice versa. So that's all you need here. You just say, okay, there's, every node is one thing or the other, so you can get by with 1 extra bit of information, which is less space than you'd need to store the entire height for an AVL tree node. So don't get too confused. We're going to be drawing all sorts of different colors. In practice with code, you just have some sort of flag you set to either 1 or 0 or whatever else, and then that's, red or black. The other issue here is that all null pointers are black. Or in other words, a pointer to a null is the equivalent of a pointer to, well, I shouldn't say equivalent, let's say it will be treated the same treated as a pointer to a black node in our cases. And that's the only reason we have this definition, because otherwise what we would be saying all the time is if we're looking at some particular pointer to a node, and if it points to a red node, we do one thing, and if it points to a black node, we do something else, and if it points to null and there is no node, then we do a third thing. But on all cases where we point to null, we'll be doing the same thing as if we had pointed to a black node. And we'll kind of talk about that when we talk about our cases a little bit, the various cases for insert and removal. But that would be why we have this definition, because it'll turn out that whenever we point to null with some pointer, well, we'll do the same thing that we would have done if that pointer had pointed to a black node. And so we'll just say, okay, well, all nulls are going to be considered black nodes, or pointers to null will be considered pointers to black nodes. And that way, when we do the matching of our various cases to decide what exactly we want to do, we'll keep that rule in mind. The third property is that any red node has 2 black children. Now, they could be null, so what this really means is no red node has a red child. A red node could have 2 black children, but they would, if they're both null pointers, they'd both be still considered black children due to rule number 2. So all we're really saying here is we don't have consecutive reds. Whenever we have a situation where there's a red node and its parent is also red, we'll have to fix that. And then for every path from root to a leaf has the same number of black nodes. And that's what we'll be dealing with here. The idea that when you follow some path from a root to a particular leaf, if you count the black nodes along that path, which might include the root and which might include that leaf, if you count the black nodes along that path, you'll have a certain number of black nodes. Now, if you follow a path from that same root to any other leaf, there'll be the same number of black nodes on that path. And so there's sort of no matter what leaf you go down to, you're going to encounter the same number of black nodes. There's a reason for that, and we're going to discuss that now, but these are going to be the 2 properties we try and keep intact. These are just going to be naturally, property 1 and 2 are just a natural part of the structure of the tree. Every node will have some color. We consider the nulls to be black. And then properties 3 and 4 are what determine a red-black tree. And if property 3 is violated, we need to fix the tree so that it isn't violated any longer. And if property 4 is violated, we need to fix the tree so that property 4 isn't violated. Similar to, if you think of a B tree where we said if the number of nodes drops below b plus 1 over 2, if the number of children in a node drops below b plus 1 over 2, that was something we had to fix. And if it was greater than b, then that was something we had to fix. So likewise here, there are certain properties that need to be the case for the red-black tree, and if what we do violates those properties, we'll need to repair that situation. So let's go back to this picture for a moment. And what we're basically saying with this red-black tree is there's going to be conversions. So this is the 2, 3, 4 node. Now when we draw these similar nodes in a red-black tree situation, a 2 node and 2, 3, 4 tree will continue to be drawn like that in a binary search tree, our red-black tree. If it's a 3 node, we're going to basically draw it like this, where you either have A with B as a red right child, and then the 3 pointers, the 3 children left of A, between A and B, and to the right of B will be drawn here. Alternatively, you may have had B as the root of this tree, with A as a left red child, and then the pointers would have been, that's the one to the left of A, that's the one between A and B, and that's the one greater than B. So you have two different options for this 3 node. It's either tilted with the red node to the right or tilted with the red node to the left, in which case then, B is the root and A is the left child, as opposed to A being the root and B being the right child. But that's what we're dealing with here. So we're saying the 3 node will be represented in one of these two ways. We're not going to just stick with one or the other. Just the natural manipulations of the tree will result in some of the 3 nodes looking like this and some of the 3 nodes looking like that. And then a 4 node will always be represented, whatever the middle value of the 4 node is, that would be your root of your little subtree we're going to draw here, with A as a red left child and C as a red right child, and then the 4 pointers, the 4 pointers to subtrees, would be 2 off of A and 2 off of C. So when we talk about building a red-black tree, all we're saying is imagine a 2, 3, 4 tree that you may have built. And when you built that, once you build it, then simply you could convert it to a red-black tree by saying keep the 2 nodes the same. Your 3 node would be converted into one of these two. And your 4 node would be converted into this. And that will be how our red-black tree works. We have to show you kind of a larger example at the moment, but that would be the basic idea here. And that's where these red children come from. What we're saying is when a node is red, remember our rule, no red node will have a red child. Every red node has 2 black children. So what we're saying here is, let's consider the black children, the black nodes, to be sort of the identifiers of these 2, 3, 4 kind of nodes. This will be conceptually what we're doing. The red-black tree will be the actual implementation. And what we're basically saying is, think of these 2 nodes as representing one node. Whenever you have a black node and it's got a red child, then those 2 are part of the same node. Here, likewise, you have a black node with a red left child. Those 2 are part of the same node. Here you have a black node with 2 red children. All 3 of those are part of the same node. But you always node ends there. Here you say, okay, if this is not a case where you have a black node with 2 red children, if you've got a black node with 1 red child and the other one's black, and then the 2 children of the red node have to be black, well, then there's your 3 children of the overall thing I've circled in blue. And likewise here, you have one red child of B, a black child of B, and then the 2 children there also have to be black because all the children of a red node are black. So these 3 are your 3 children of the 3 node. And then in the case of the 4 node, one of these reds has 2 black children, and the other one of these reds has 2 black children. So you have the 4 black children you need for your 4 node. So that's the idea. Basically, every node in the tree gets converted to some node that contains 1 black node and 0 or 1 or 2 red nodes. In this case, you have 1 black node and no red nodes. Here you have 1 black node and 1 red node, and here you have the 4 node gets converted into a little subtree with 1 black node and 2 red nodes. So every single node in the 2, 3, 4 tree will be represented by exactly 1 black node in the red-black tree. And this will be clear when we see a full example, but that's where this property comes from then. Every node in the 2, 3 tree, all the leaves are on the same level. And now, if every single node in our 2, 3, 4 tree, which will basically have this be the same idea, all the leaves will be on the same level. If all the leaves are on the same level, then if every single node in the 2, 3, 4 tree gets converted to some little structure like we see on the previous page, but with exactly 1 black node, well then all the leaves in the red-black tree will have encountered as you move from root to leaf, you encounter exactly 1 black node for every node in the 2, 3, 4 tree. And so if the number of nodes going from root to leaf on the 2, 3, 4 tree were the same, then the number of black nodes in the red-black tree along from root to leaf will be the same. And we'll talk, again, this will be clear when I draw a full picture, but that's what will be going on here. 2 other things I want to mention about this. Notice that in any of these 4 structures, the 2 node, either version of the 3 node, or the 4 node, the black node is always at the top. and the red node will be the child. You'll never have a situation where I would have represented the 3 node here this way. I never would say make the red child A and then have it have a black child B and say, okay, these two are part of one node. So you have these children here, and you say, hey, great, now this is one node. You'll never do that. It's always the black node that's at the top, and that way I know when I point down here, the 4 node, each of these pointers was pointing to a new node. Well, likewise, each of these is pointing to a new circled blue collection here. If I want to circle this, maybe I can do the same thing. So each of these is pointing to one of these 4 patterns. We won't actually do that. Likewise, each of these is pointing to one of those patterns, and likewise, each of these is pointing to one of those 4 patterns, and likewise, each of these is pointing to one of those 4 patterns. So your red nodes always are saying we're pointing to some new node here. This is AB. These pointers would have been pointing to brand new nodes, and therefore they must be pointing to the black nodes that are at the heads of these structures. Likewise, here with A, these two would have been pointing to new 2, 3, 4 nodes. So these pointers are pointing to new circled blue structures, which all start with the black. And so the 2 pointers of A have to be pointing to black nodes. And likewise, each of these 4 pointers was pointing to a new node. Therefore, each of these is pointing to a new blue node circled blue structure, and so each of these must be pointing to the black node at the top of them. If you're going to have BA as a subtree, you would have said, okay, well here's, well I can't do that because I use the same letters. But if you had this kind of structure as this subtree, then you would have said, okay, there's a black node here, followed by a red one. And then here maybe we have just a 2 node, and maybe here we have a 3 node tilted the other way, so there's a black and then a red as the right child. And then maybe here we point to another 4 node. And so you would have a black node there, followed by 2 red nodes as children, and then each of those red nodes has 2 black children. So that would be the idea here. Here we say this points to a 3 node, that points to a 2 node, that points to a 3 node, that points to a 4 node. And you would have had that here. This would have been a 3 node, this would have been a 2 node, this would have been a 3 node, and this would have been a 4 node. And you would have had the corresponding pointers from there. I do need to now draw a full example tree to show you, but that's why we know the red nodes would always have to have black children. We say, well, the red nodes are pointing down to what is conceptually new nodes in the 2, 3, 4 tree. Each of the reds points down to one of these new nodes, and since that new node is rooted by a black node, well then you're always going to be pointing down to black nodes from your red nodes. This also means that the root is always black, because one of these nodes, types of nodes, whether it's a 2 node or a 3 node or a 4 node, is at the top of your structure, and that means either whether it's this as your root, or that kind of setup as your root, or that setup as your root, or that setup, the root will always be black because it's always going to be one of these 4 patterns, and each of those patterns starts with a black node. So you know your root is always black. So those are some basic properties of the red-black tree. What we need to do now is look at a full example, a full picture, to give you a better idea of exactly what's going on here. So let's start here, and we say that we will have a picture. We'll have here 20 and 50 and 80. This is the 2, 3, 4 tree I'm drawing. So the root's a 4 node, and I have now 5 and 10, and I'll have here 2 and 7 and 8, and I'll have here 12, 15, and 16. So the root's a 4 node, this is a 3 node here, your leaves of that are 2, 3 node, and a 4 node. And then you'll have various subtrees here, and I'm not going to draw all the subtrees because it's only going to be this portion we're concerned with. So all the detail here isn't going to matter too much. We've got some subtrees, each of which would have 2 levels, just like the left child of 20 had 2 levels. Likewise, the right child of 20, the right of 50, and the right of 80 would also have 2 levels. Because in a 2, 3, 4 tree, it'll be just like a 2, 3 tree or a B tree. All the leaves need to be on the same level. What we want to worry about is how this gets represented as a red-black tree. So the 4 node, notice, is represented like this. Just like we do in the previous slide, we say here we've got 50 pointing to 20 and 80. That was our pattern for the 4 node. We said 4 nodes with 3 values and 4 children get drawn like that. Now the 3 node, we have 2 options for drawing the 3 node. We can either have the lower value as the root with the greater one as the left child, or right child, or have the greater one as the root with the lower value as the left child. Either way we can do things. Let's do this way first, and we wouldn't have actually picked this as we went. This would have just happened as we inserted, but just to kind of draw the tree in some way, we'll say, okay, maybe the 510 node is represented in this fashion, and then it has 3 pointers. And the first one is a pointer to the 2 node, containing just 2, and then 2 null pointers. The 10 here points to 8 and 7, and now we can say, okay, maybe this 3 node is tilted the other way. So we had here, this 3 node was 5 with 10 as a right child. The 8-7 3 node is 8 followed by 7 as a left child. So we see now this example is, let me actually do this. Here's one way to represent a 3 node. Here's another way to represent a 3 node. And then the 12, 15, 16 is another 4 node, and so that's drawn the standard way. Whoops. Just as we did with the root, we would say here we have 15 as the root of this little mini subtree with 12 and 16 as children. And now we would have said, well, now here, whoops. We would have said, now here's subtree A. I'm going to draw 80 over a little bit just to make some room here. Actually, let me, here's 80. And then this would have been subtree B and subtree C. And that's what's going on there. So here we say to the left of 80 we have C, between 50 and 80 we have B, and you can see here it's greater than 50 but less than 80. Between 50 and 20 we have A, and it's less than 50 but greater than 20. And then to the left of 20 we have this whole subtree. And again, this A, B, and C would also have been converted to red-black trees. We're not going to show the whole thing right now. We'll just focus on this one of the 4 subtrees of the root, and we'll show that. So this would have been how that whole side of the tree gets converted to red-black. You've got this 50, 20, 80 example, and maybe I can even draw that in a more nicely distributed fashion here. Let me try this. 50 in the middle, and now there. That's a bit better. So you have the 50, 20, 80 node, which is your 4 node, that's your root, and the 5, 10 node, which is your 3 node, that's the child of the root. You have then 2 is a child of 5, 10, 8 and 7 together are a child of 5, 10, and 12, 15, 16 together are a child of 5, 10. Remember, if it's a red node, that means it's really, in the 2, 3, 4 node, 2, 3, 4 tree conceptually, a red node is part of the same node as its black parent. So 7 is really part of whatever contains 8, and we can see that's the case. 12 and 16 are really part of what contains 15, and we see that's the case. 10 is really part of what contains 5, and we can see that's the case. And 20 and 80 are really part of what contains 50, and we can see that's the case. So that's what we're dealing with here as far as red-black trees go. And so whenever you get confused about red-black trees, you simply, in your mind, merge any red nodes with their black parents and convert it all back into the 2, 3, 4 tree. This is how we actually implement it, but conceptually this is kind of what we're doing. We're just able to do this without having special types of nodes. We can do that using an ordinary binary search tree idea. And that's what the red-black is really doing. It's implementing this tree using just binary search tree nodes. And so the coloring things red or black is a substitute for having to actually implement 2 nodes and 3 nodes and 4 nodes. So if we go ahead and note, well, first we've already explained why we'll never have to have 2 red nodes in a row. We saw this here, that any red node is going to be pointing then to a new circled blue type of structure, a new 2 node, a new 3 node, a new 4 node, and those always start with black nodes. So any red should always be pointing to a black node. Also, if every one of these nodes in the 2, 3, 4 tree is represented by exactly one black node in the tree. Well, if in going from a parent to a leaf, we have here one black node, which is the root, and then moving down to its child, we have a second node, and then moving down to the leaf, we have a third node. Well, if each of those three nodes is represented by a single black node in the red-black tree, we should encounter three nodes too. 50 is the root, it's a black node. We go to 20, if we're going to look for 16, for example, we go to 20, then to 5, 5 being the black node representing that node. Then we go to 10, then to 15, and there's now the black value representing that node, and then 16. So in going from 50 to 16, I encounter three black nodes, just as in going from the root to the leaf containing 16 here, I encounter three black nodes, namely the root, 5, 10, and 12, 15, 16. And likewise, if I went to the node containing 2 in the 2, 3, 4 tree, I would have encountered the root, 5, 10, and 2, and likewise here, I encounter 50, which is the black value for the root, 5, which is the black value for 5, 10, and 2. And every leaf you look at, going to 2, you encounter 55 and 2. If you want to go to 7, you encounter 55 and 8. If you want to go to 12, you encounter 55 and 15. And if you want to go to 16, you encounter 55 and 15. Every path down to one of these four leaves contains exactly three black nodes, just like every path down to either going down to 2 or 7, 8 or 12, 15, 16, that will contain three actual nodes in the 2, 3 tree. Here we contain three actual black nodes. And that then was the point of this last property. Every path will have the same number of black nodes as you go from root to a leaf, precisely because every path has one black node representing one of the nodes you came from. So if you had three nodes in going from root to leaf here, you'll have three black nodes in going from root to leaf down here. And that's our setup. So that's a red-black tree. Now, what's interesting is attempting to manipulate this red-black tree, and when we do so, what we're basically going to be trying to do is to keep the 2, 3 algorithms intact. That is the way we would have a no overflow or overflow in split cases for the, whoops, draw that back in. The no overflow or the split cases for insert, the way we'd have the no underflow or steal or remove case or combined cases for remove. Those are the things we're going to be attempting to do here. And so that's going to be our ultimate goal. I'm going to copy this so I can paste it back in later on. Copy. And there we go. So let's consider insert now. In considering insert, we're going to say firstly, the first thing we will do is a binary search tree insert. Once we do that, we will make the new leaf red. And the question is, well, why would we have to make the new leaf red? And the answer is, well, think what would happen if we made the new leaf black. If, for example, I want to insert 1 into this tree, well, 1 is less than 50, less than 20, less than 5, less than 2. I would attach 1 as the left child of 2. That's how binary search tree insertions work. But now suddenly, the path down to the node containing 1, which is a leaf, has 4 black nodes. And we only want it to have 3. And if you consider the 2, 3 example here, or 2, 3, 4 tree, what we would have done is we would have said, well, 1's less than 20, 1 is less than 5. We would have inserted 1 into that node with no overflow. So what we would want is to have 1 and 2 be in the same node, and yet here, by virtue of 1 being a black child of 2, 1 and 2 are considered to be in different nodes, as if we had done this. Whoops. As if we had done this, which doesn't make any sense. What we really would have done is not had 1 as a child of 2, but put 1 inside the same node as 2. We would have had this sort of situation. And we recognize that by saying, okay, 1 and 2 are part of the same 3 node. How did we represent that? Well, we said one of the nodes was black, and then its child was red. This is how we would represent 1 and 2 being in the same 3 node. You have a black 2 followed by a red child 1, and that follows the 8-7 pattern as well. Here we have a 3 node, here we have a 3 node. In both cases, you've got a black root and a red left child. Or even in the 5-10 case, where you have a black root and a red right child. Same idea. So you want to color that node red. If it were colored black, you'd now suddenly on this path would have had 4 black nodes, 55, 2, and 1. Now you make sure you still have 3 black nodes. You've added a new node, but by coloring it red, you haven't changed the black height. So that's why you have to make the new leaf red. You can't, you don't want to make it black because, making it black would violate the rule about the number of black nodes along a path from root to leaf, namely that it has to be the same as the same number of black nodes and along any other path from a root to any other leaf. And so all the other paths would still be 3, 55, 15, down to 16. If we're going down to 7, you have 55 and 8. But now suddenly you'd have 55, 2, and 1 if 1 were black. One path would have 4 black nodes, the others would have 3. That's not allowed. So the new node has to be red. So now we will call the new node X. And we will basically then say, as long as 2 things are true, firstly, X is not the root. We'll move X up in the tree sometimes. And X's parent is red. As long as those 2 cases are 2 things are true, we'll run the inside of our while loop, which will consist of basically 2 cases. With one of the cases having sort of 2 parts, but 2 major cases corresponding to the 2 major cases of the insert algorithm, namely a no overflow case and an overflow case. So we'll have that. Then, once we exit that, we exit either because X is the root or because X's parent is red. I'm sorry, X's parent is black. If we've exited because X's parent is black, we would just end up stopping. Everything would be cool. If we exit because X is the root, well, in another case, we want to make sure when we're done, we want to make sure when we're done here, the root may have been red, and that's why we left. So we want to make sure the root is colored black. We have to look at the 2 cases yet, but that's what we're dealing with here. We will say, when I leave this while loop, I assume the root is colored. After I leave the while loop, the root gets colored black. So if I left because X reached the root and the root was red, you color it black. And that will be the situation here. So let's put the original picture back. We said, okay, well, there wasn't really a 1 here. This node was a just ordinary node here. And this node was... So that's our original picture. And we're going to show a few situations about this insert. Firstly, let's show 4. If I'm inserting 4, well, that's just like inserting 1. 4 is less than 50, less than 20, less than 5, greater than 2. We insert a leaf, and we always insert leaves as red nodes. So we just insert 4 there. Inserting 4, as we just said with 1, we say, well, that's just like if we had inserted 4 into this node. We make the 2 node containing the number 2, a 3 node containing the numbers 2 and 4. And that's exactly what we've done in this case. We've made this a 3 node containing the numbers 2 and 4. So there's an example where there is no overflow and we just stop. And what would have happened here, the way we would have done that, we would have said we insert 4, we would have called this X. That's what we'd said with our insert algorithm. Call the new node X. So that's what we did here. And now we say keep going as long as X is not the root, which is certainly isn't. 50 is the root, and X is not 50. And X's parent is red. Well, X is not the root, and X's parent is black. So we quit. We're done. And then you just would say color the root black, but in this case it already is. Whoops. So we're all set. So this is the insert. I kind of want to draw the whole insert here. That's all there is to insert, except we actually have to talk about what these 2 cases do. But that's the idea behind insert there. So, to show another example, basically what we're saying here is when you insert a new node as a red node, we already said you won't affect the black height. And then if there is a red node with a red parent, that needs to be fixed. So for example, let's say we inserted 6. If I inserted 6, 6 is less than 20, 6 is greater than 5, so this number is going to be between 5 and 10, and 6 would have been inserted right into this node, making it switch from a 3 node to a 4 node. We would have had the node 7, 8, we would have put 6 in there, and we would have gone to a 4 node, which for the sake of a 2, 3, 4 tree is not overflow. In the 2, 3 trees we looked at in more detail, that would have been overflow. The 2, 3, 4 tree now, so it's safe to insert 6 into here. Inserting into this node would be a problem, but you can insert into a 3 node, and that just makes it a 4 node, which was, in this example, perfectly legal. So the equivalent here is inserting 6 as the left child of 7. We say it's less than 50, less than 20, greater than 5, less than 10, less than 8, less than 7, and 6 gets inserted there, and we say, okay, call this x. Let me erase the old operation here. So 6 is x, the new node, it's red. And you notice 6's parent is red as well. And that's no good. So we've got to look, kind of now mess with this a bit. We know at this point 6 has a grandparent, because the root has to be black. We had spent that time in the previous discussing why if the root of every one of these 4 circled blue patterns had to start with a black node, well, one of them was the root of the tree, so the root of the tree started with a black node. If you had a 2 node as the root of your tree, well, it starts with a black node. If you have a 3 node as the root of your tree, well, each of those starts with a black node. If you have a 4 node as the root of your tree, well, that starts with a black node. So the very highest node of your tree, the root of your red-black tree, is going to be black. We know that for sure. Oops. So given that, we know that if your parent of x is red, that's not the root. Because if it was the root, it would be black for sure. So you know you've got a grandparent. And that means we're dealing with this sort of situation here, where you say, I've got a grandparent, and so now it's just a matter of saying, all these 3 are part of the same node. Because remember, red children are simply part of the same node as their parent. 7 is part of the same node as 8. Now since 6 is a red child, 6 is part of the same node as 7, which is part of the same node as 8. And that says we've got this situation here, which I can redraw with a new value. I'm saying here, I've just inserted 6 into this tree in addition to the 7 and 8 that were in this node earlier. And so that's my new 4 node. And that's sort of what we're drawing here. We're saying we've got 6, 7, and 8. Notice that would not quite work if we had inserted, say, 11. If I had inserted the 11 here, well, now we've got a problem in that, yes, I could technically circle 11, 12, and 15 and say, hey, there's a 4 node, 3 values, and we have to deal with 4 children then. But it's leaving off 16. 16 was part of this node. 12, 15, and 16 were a 4 node. They were all part of the same node. And now 11, if I was going to insert it, would be part of that same node as well, and we have to deal with that. Here, I inserted 6 as part of this node, and so we went from 7, 8 to 6, 7, 8. Here, I'm implying going from 12, 15, 16 to 11, 12, 15, 16. And you could draw the same thing up here if you were inserting 11. So how do we detect that? Because certainly, if I'm inserting, I really should say, well, if I'm inserting 11 here, this whole thing is really overflow. So this whole node, whoops. This whole node, dang, sorry. Problem with this is it stretches like that. This whole node, all 4 values would be considered part of one node. 12 is part of the node above it because it's red. 16 is part of the node above it because it's red. 11 is part of the node above it because it's red. And that would have represented this overflowing node. If you throw 11 in the little side there, that's an overflowing node. 5 values. 4 values, 5 pointers. But this node is not overflowing. You're allowed to have 6, 7, and 8 in the same node. And the way we tell the difference between the two is, well, remember, 4 nodes have to have 2 red children. You have the center piece, which is the root of that little subtree there, the middle value of your 4 node, and then it has 2 red children. Whereas your 3 node will have 1 red child, but it'll also have a black child, which in this case is null. So let me get rid of these blue circles now. And that's the situation we're dealing with here. We're saying 8's right child is null, which means it's a black node. If 8's right child had been a red node, then we would know for sure, okay, 8 has 2 red children, so both of those children are part of the node 8. Just like both of 12 and 16 were part of the same node as 15, and we saw that up here. Likewise, if 8's child had been red, it means 7 and that child are both the same node as 8. and we would have had 3 values to begin with, and 6 would have been a fourth. But that's not the case here. Since 8 has a black child, we know that that's one of these nodes here off of 8. And then 7's also got a black child, and that's this. And now 6 has 2 black children, and those are the other 2 null pointers. We've got 4 pointers and 3 values on this node. And so that's what we want to inspect. We want to say, basically, I've just inserted a value. If my grandparent's other sibling is black, then I know me and my parent and my grandparent, 6, 7, and 8 here, X's parent and X's grandparent, are all part of the same 4 node, and we simply need to readjust the way that 4 node is tilted to follow the rules of the red-black tree. On the other hand, if your grandparent's other child is red, well, that means your parent's sibling, and your grandparent were all already part of a 4 node. Now you're tacking on yourself to the party, and that means you overflow everything. And those will be the ways we know the overflow cases. When you attach to a 2 node, like we did with 4, you're simply saying, okay, you go from a 2 node to a 3 node. Your 2 node was black, and it gains a red leaf. When you attach to a 3 node, making it a 4 node, you could have done that by maybe saying attach 9. We could have had a situation here where we said, okay, we're going to insert 9, and so 9 becomes a subtree of 8. Let me draw that here. If 9 had become a child of 8, we would have inserted that as a red node, and then we would have said, oh, we got 7, 8, and 9. And that's just a 4 node, 7, 8, and 9 with 4 children. And that wouldn't have been a problem. So here, the new value x has a black parent, we'd stop. And that's the equivalent of saying your 3 node was already tilted this way. You had this original 7 and 8 node. You're saying, okay, I had 8 tilted with 7, and that represented the 2 node 7 and 8. And if I inserted 9, I'm inserting it on the other side of what was already the root. So inserting 9 here is harmless. You just do that. The problem with what we're really doing is 8 represents, in the red-black tree, 8 is the root, 7 is the left child, and we're not inserting as the other child of what is black. We're inserting more values onto the same side of the root here. If 8 is the root and 7 is the child, now we're attempting to insert another value on the same side as that. So we had 8 and 7, but we're inserting 6, meaning 7 should really be the root of this 4 node, not 8. It was okay for 8 to be the root when it was just 8 and 7, when it was just a 3 node. But now that it's a 4 node, 7 has to be the root. Just like our 4 node up here, 50 was the root, and then our 4 node here, 15 had to be the root. If we're turning this 7, 8, 3 node into a 6, 7, 8, 4 node, 7 must be the root. That's how 4 nodes work. The middle value is the root, and then the thing to the left of 7 and to the right of 7 become red children. So those are our cases. We're distinguishing correcting the lean of a 3 node from having inserted into a 4 node and caused overflow. And the thing that separates these is the other child of the grandparent. Is it red or is it black? So when we talk about our 2 cases, those will be our 2 cases. We're going to say now case 1 when we're inside the while loop. We say, okay, x is our node we are working with. Whoops. Working at. X is the node we're working at. And then we say, we also know x is red, x's parent is red, and since x's parent is red, we know x's grandparent is black. This isn't even case 1. This is just, we know these things to be true. At this point, when we're in the while loop, we know x is red, we know x's parent is red, we know x's grandparent is black. So we say, case 1, the sibling of x's parent is black, which also means it could be null. And then case 2 will be that the sibling of x's parent is red. If the sibling of X's parent is black, that means, okay, X's parent and X's grandparent are part of the same node, but the sibling of the parent is not really involved in that. Whereas if the sibling of X's parent is red, that means the sibling is involved, and that's what we saw here too. If this is X, let me not circle this. If this is our X here, here's your parent, here's your grandparent. This null pointer is the sibling of X's parent. X's parent is 7. This null pointer is a sibling. If it's black, then that means that node is not part of the parent node until you have a 3 node here. On the other hand, if this were X, if we inserted 11, 16 is the sibling of the X's parent being 12, so 16 is the sibling of that. Well, if the sibling is red, it means that not only was the parent and a grandparent already part of one node, we saw that here too. 7 and 8 were part of one node, but since 8's child is black, 8's child is not part of that node. Here, 15 and 12 are part of the same node. Since 16 is red, 16 is also part of that node. So 12, 16, and 15 were already a 4 node together. And now the insertion of X has made that overflow. Versus here, 8 and 7 are part of the same node, but the child's not part of it, though. So 8 and 7 are part of a 3 node. By inserting 6, we're making it into a 4 node. And so case 1 here, we simply say if we've got case 1, what we will do is a rotation on the grandparent. We say if X, I should say if the direction you go to get to the parent from the grandparent, having trouble spelling today, is equal to the direction you go to get from parent to X, and I'll put case 2 on the next page. Then what you're going to do here is a single rotation, else you're going to do a double rotation. And we also say single rotation with some color changes. And here you have double rotation with some color changes. And that's what's going on here. You're saying that in this case, I'll be able to do a single rotation on the grandparent. And so we're saying if the direction you go to get to the parent from grandparent is equal to the direction you go to get from parent to X. What this is saying is, here's my grandparent, which is 8. I go to the left to get to the parent, and then left again to go to X. So these are all in one linear line, one line. That's your single rotation case, because it'll move 7 up and 8 down, and that's what we want. That's going to be cool. So I'm going to get rid of 11 now. We don't need this. This is just our example we illustrated earlier. This is what we're trying to do, insert 6. And the single rotation will fix this up. What we're basically saying is, what this has forced us now to rearrange the way the 2 node is handled. We're going to take this subtree and we're going to draw it so that 7 becomes the root, and 6 becomes the left child, and 8 becomes the right child. And that's what we want to do here, is color things that way. We want to do the rotation, but in the process of doing the rotation, we want to say, well, now what we will do is make the parent of X black, and we want to make the parent of X red. And that's what happens here. So we're going to say the single rotation with some color changes is going to be, beforehand we would have said parent, actually let me kind of draw it this way. I want to give you the single versus double first, but let's say this is case A here. Sibling, let me put that in a different place. This is your case 1A. So you already know the sibling is black. Now if the direction you go is the same in both cases, then you color X's parent red. You color X's, I'm sorry, it's already red. You color it black. Let's try that again. You color X's parent black. You color X's grandparent red. And then once you've colored X's parent black and colored X's grandparent red, you do a single rotation away from X. That is, i.e., X's parent becomes the root of the subtree. So these are your 3 steps. If you hit that situation we saw where you move to the left to get to your parent from the grandparent and then to the left again to get to your X, or if you were at the grandparent and you went to the right to get to the parent and then to the right to get to X, in that case you make X's parent black, the grandparent red, and then you do a single rotation. And that's what we see in this picture. We have this situation. From the grandparent to the parent you're going to the left, and then you go to the left again to get to X. So you're saying make this black, the parent of X is black, the grandparent is red, and then you simply do the single rotation away from X. That is, the parent of X becomes the root 7. Rather than towards X, rather than pushing nodes this way, you're putting nodes this way. So if this stuff is on the left, you're doing a right rotation. If this was on the right, you do a left rotation. But this is what you end up with. You're saying, I've got a 4 node here, 6, 7, and 8. It's just that it's the leftmost value, 8, that is currently considered the root when I draw this in my red-black tree, and I want 7 to be the root. So I'm simply rotating 7 upwards and 8 down, and all I get then as a result of that is I say, well, I also need to switch 7 and 8 around in terms of color. I don't want a red root and a black child, I want a black root and a red child. So that's how we solve this. We say, if you've got this situation where you're a red node and a red child and your sibling's black, you're basically correcting a 4 node, the tilt of a 4 node. You want to make it go from that to that. So you color X's parent black, color X's grandparent red, do your rotation, and that's how you end up. And that's basically case 1A. Case 2A, or I'm sorry, case 1B. This is 1A, and we said here was the A case. Case B is, whoops, this is case 1B if the grandparent to parent direction and the parent to X direction are different. It's kind of messy there. Are different. Well, that's what we are dealing with if we insert 3. So let me go ahead and we're happy with this now. Let's keep this, fix this here. We've created this situation out of it. So we say, okay, now 7 is this root, and we have here 6 and 8 as values. And that's where I'm just going to kind of get rid of these nulls, but, you know, kind of clean up the picture a bit. But that's what we're dealing with here. We've inserted 6 successfully. 6 is now part of the 2, 3, 4 tree, and we represent this accordingly. 6, 7, 8 is a 4 node, 7 is the root, 6 and 8 are the red children. What if we insert 3? If we're looking at the 2, 3 picture here, 3 is less than 20, less than 5. 3 should go there, 2, 3, 4. In the red-black tree, 3 is greater than 2, less than 4, and 3 gets inserted here. So again, the parent of 3 is red, but you can't do a single rotation on the grandparent. That's just going to move 4 and 3 around. What you want to do here is you're saying since 3 is between 2 and 4, 3 should be the root. And this is the same as saying when we did our AVL trees that this node should be moving up to the root. That was the node that helped us split. In the case we just did, you had 6 followed by 7 followed by 8, and you said a single rotation would do because the child here, the 7, that should be the root. Here you need a double rotation because it's this lowest value, not the child of your subtree root, but its child, that should be the what's between them. And that's why when you change directions, you say 4 is to the right of 2, 3 is to the left of 4. That means 3 is sort of in one of those inner subtrees like we had with the AVL tree. When things are the same direction, 7 is to the left of 8, 6 is to the left of 7. That was an outer subtree that 6 was in. And we go back to the outer and inner definition that we had for AVL trees. In this case, we want to move 3 up to the top, so we ultimately need a double rotation. We want to move 3 up to where 4 is, and then move 4 up to where 2 is. And all we need to do firstly here is say, well, this is our x. The first thing we want to do with x is that we want to say, first thing we do here is we say, we need to recognize this is the picture we want. So we're going from here. We say this is ultimately the picture we're going to want here. We have 3 and 2 and 4 there. Let me erase the rest of this crap. So I have 2, 3, and 4. I want to rotate it to get this situation. And so the double rotation will do that, but we still have some color changes we need to worry about as well. And so we need to consider how we're going to make those color changes happen. What we're going to do to make those color changes happen is we say, well, I first want to do the, since the single rotation I talked about before will basically make 3 black and 2 red, what I could, in a sense, do is simply rotate here and then do the case I just did. So I could have said, step 1 will be, I have 2 followed by 3 followed by 4. And then once I have that, I sort of, in a sense, I'll make this my x and do the previous step, and that would make 3 black and 2 red. And that's all I'm doing here. I'll say, okay, if I hit this case, I do this rotation, and then I make this x, and I do the other rotation. But since we know these are red, what we're really doing in a sense here is we're saying, make the grandparent red, make x black, and then do a double rotation on the parent. And that ultimately is what accomplishes the same thing here. We say the 4 node is going to stay red. This 3 node is going to become black because that will become the root. The 2 node will become red because it becomes a child. And so effectively, if you combine the two, that's what's going to happen. You can either think of this as just do your rotation, and once your rotation is done, make 4 your x instead and apply the previous case, which will give you this. Or you can think of it all as one operation, make 3 black, 2 red, and do a double rotation. That's how I'll write it. But the 1b is going to be, I'm going to write it both ways. You can either do it this way, which is make x black, make the grandparent red, and then do a double rotation on grandparent. And the double rotation, again, has to be in the appropriate direction. In this case, the double rotation here is going to be overall in that direction. We do a double left rotation, which means rotate to the right on the right child, and then left overall. But that's because if you did a double right rotation, things wouldn't work. So you're doing the double rotation that's meant to move x up to the root. And that's why we can do this. Whoops. What we say here is, have the double rotation of the grandparent, do the double direction meant to move x to the root of subtree. And that should help you decide whether to do the left or the right double rotation. Whichever one is going to actually move x upward, that's the one you want to do. And we have, the two mirror image case to worry about here. The other way to think about this, if we think about this as one way to visualize it, the other way to visualize it is to say, do a right rotation, or, and you think about this a different way here. So this is one way to think about it. Another way to think about it is to say, do a rotation on x's parent to move x to where parent used to be. Call the former parent of x, and then do step 1a. So that's another way to think about it as well. Dang, sorry about that. Those are two different ways to approach this problem. They do exactly the same thing. I got a page in the way, unfortunately. So we're basically saying here, you either think of this as coloring x black, coloring the grandparent red, and doing a double rotation, or you think about it as just do a single rotation on the right child, and then once you've done that, make your former parent of x, x, and now do case 1a. Either way, what we'll end up with is this tree in that place. This is not easy by any means, but as you do examples, this will be like the AVL tree. Once you do enough examples, everything will be cool. So, we're running low on time here. I've really got to finish this up. This is what we end up with here. The only other question now is what happens when you insert into a for node. That's the overflow case you have. So we've got this now. And you say, what happens? Let me redraw this node, blah, 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 blah. And you've got here 2, 3, and 4. So you say, here's this node. What happens when you come along and you insert 17? Inserting 17 here, you insert 17 as a new node, but this is just like the insert 11 case we looked at before. Your parent's sibling is red. And that's what we have here. Case 1 was, we always know the sibling of x's parent is black, and then it's just a matter of which direction is appropriate. Are you doing a single or a double rotation? Case 2 here is, case 2 will be siblings parent, or I should say, wrong way around, x's parent's sibling, not sibling's parent. X's parent's sibling is red. This is the overflow case. And all we do to fix the overflow, if we kind of jump back to the picture, is we say, well, if I had overflow here, if I had 12, 15, 16, and 17 in one node, and let me draw that out here. I'm going to draw 17 as a blue value. If I had 12, 15, 16, and 17 in one node, that's overflow, what I'll do is split. I would say have 12 be in one half, have 16 and 17 be in the other half of the split, and 15 will move up. And 15 moves up because this parent needs to gain both 15 and the new child, 16, 17. So that's what would have happened there. If there was an overflow, you split it into 2, the middle value moves up into the parent. And we will accomplish that in this case. The way we accomplish this is simply by saying, well, if this is your situation, you're going to color the parent of x and its sibling black. So this is going to become black, and the sibling will also become black, and the parent becomes red. So if I redraw that, 12 and 16 become black, 17 becomes red. Let me redraw that in a nice way here. We say, okay, we now know that 15 is red. That was the root of this node. And we say 12 is one child and 16 is another child. So see what we've done here. By taking that 4 node, which used to be represented like this, which meant 12 and 16 were part of 15. By converting it to what we've got now, what we're saying is, well, instead of 15 being part of a node and then 12 and 16 being part of the same node, 12 and 16 are completely independent nodes, and 15 happens to be something in the parent that points to both of them. It means now this has to be red, of course, as well. But it means we've changed it so now 15, by making it red, we've made it part of the node above it. 15 has moved up into the parent, and by making its children black, it means, okay, we've broken those 2 pieces off. 12 and 16 are now no longer part of the same node as 15. 12 and 16 are children of 15. But that's exactly what we have here in the altered picture. If I now erase 15 from that little area there, I say 5, 10, and 15 are part of one node. 12 and 16 are children of 15. And then 17 is just part of the same node as 16 here. So that's all that happens here. We simply say, in the case of overflow, we say parent of X and its sibling become black. Grandparent of X becomes red, and then we'll say X points to what used to be the grandparent. And this will be our continue case. And that's it. That's insert. Let me kind of finish this off here. It's a continue case because in this picture, we say, okay, well now this becomes when we talk about when we mean X. And now we continue. We say, hey, we can't stop because X does still have a red parent. Is the parent sibling black? Yes. So that was case 2. I'm sorry, that was case 1. When the parent sibling is black, that was case 1, which meant there was no overflow. And we can see 5, 10, 15 is a perfectly legitimate node. That was no overflow. And so all we had to do is we said, well, now that we have to worry about perhaps doing a rotation to fix this, that would be a single rotation. So we would have made 10 the root, 5 would have been the left child. This is our case 1a again, when the grandparent's child and the parent's child are in the same direction. And so we would have said make 10 black, make 5 red, and now do a rotation. And doing that rotation would have, if I can kind of quickly toggle this, pointed 20 to 10. It would have pointed 10 to 5. And then 3 and 7 would have been black children of 5. And this would be 10 here. It's hard to kind of draw the situation, but that's what we would have had here. We rotated 10 up to become the parent of that subtree, 5 down to become the child of that subtree, and then 3 and 5 are children of 7. And that's what we have here now. Notice this is the 5, 10, 15 is your 4 node here. 10 is the root, 5 and 15 is children, and the 16, 17 node, the 12 node, the 7, 6, 8, and the 3, 2, 4 as your children of that node. And that's that. That's our cases here. Our root special case, when the root splits and 50 moves up, 50 would have been red and you simply color it to black. And we had handled that here. We said when we finally leave this root, you color the loop, you color the root black. But other than that, that's our case 2. You simply recolor some things and X points up to the grandparent. And that may continue all the way on up to the root, otherwise you'd stop. So that's insert. Case 1a, it's designed to say, hey, 1a and 1b mean you've created 4 node, you just have to tilt it in the correct direction again. So you do rotations to fix that. And that's a no overflow case. Case 2 is the overflow case, so you represent the splitting of the node by a recoloring, and then you say, okay, well now check my grandparent of x, which is the parent in the 2,3 node. This is not easy by any means. We're going to spend the whole next lecture talking about insert, or remove rather, but this is what you want to focus on, is the idea of all the manipulations we're doing having some parallel for our 2, 3, 4 tree messings, the split or the no overflow there. But for now, that's the insert example. You'll get a chance to see many more examples and work through, full trees, but that's the situation here. That's it for now. I'll see you next time when we talk about remove.